Hello everyone, welcome to my channel. Today we are going to learn about binary search tree under data structure. So you can see over here, binary search tree looks like this. This is a image for binary search tree. So what we will learn today, what is binary search tree? And we will see why binary search tree is used. And lastly, we'll see one example on binary search tree. So what is binary search tree? Binary search tree is a node-based binary tree data structure which has following properties. It is a data structure. Data structure is nothing but a container for storing any type of data such as float, integer, character, string, etc. Okay, in a organized and efficient manner. Binary search tree is also one of the data structure which is used to store the data, and it is a tree based data structure which has a nodes. So when you use this data structure, it looks like a tree. So it has the following properties. Left subtree of the node contains only nodes with keys lesser than the node's key. Right subtree of the node contains only nodes with the keys greater than the node's key. And the left and right subtree each must also be a binary search tree. Now what is the meaning of this? Binary search tree is a sibling of binary tree. Okay, it is a variation of binary tree only. So what was happening in the binary tree? So having one root node, this is called as root node. Okay, like tree has a root. So here also for binary tree or binary search tree, there is a root. And every root has what? Left and right child. So this is called as left child and this is called as right child. Now in binary tree, what was happening? Now suppose this was a binary tree, what would have happened over here? I can put any value. I can put over here 4, I can put over here 2, I can put over here 7. In any way I can store the values inside the tree. Only condition is what for binary tree? It should have a one root and every root have either 0, 1 or at the most 2 children. Okay, root might not have any children, it might have 2 children or it might have 1 children, like this. This was the condition for binary tree. You can put the values the way you want. I can put like this also, 2 4 7. Then I can take over here 8, I can take over here 1, then here I can take 3, here I can take 5, any values, and you can put the any way you want. Only condition was what? There should be a root node and every root node can have no child, like in this. See, this root node is not having any children, or root node can have a one left child like this. Now see, here root node is 3 and it is having the left child which has a value 5, or it can have a root node and the right child like this. See, root node is having value 8 and the right child it has value 1. Or binary tree can have two children, left as well as the right child, like this. So 2 is the root, the left child is having the value 4 and the right child is having value 7. So this was the concept of binary tree. Now binary search tree is also a binary tree, but it has some restrictions or more conditions or more strictness as compared to binary tree. Now what is the strictness in binary search tree? There is a root and it can have a left child and the right child, or it can have only a left child, or it can have only a right child or no child, like this. But what is the condition? Whenever it has a left child and right child, suppose here 4 is there as the root value, its left child value should be less than 4. It can be anything but less than 4. And value on of the right child of this binary search tree should be greater than 4. Okay, so this is a condition. Now root should have value lesser than it in the left side, that is in the left subtree, and it should have value greater than it in the right subtree. So if more children are there, then you have to put it in this fashion only. Now suppose 3, if you further wants to extend, now 3 can be considered as a root. Okay, and 3 can have 2 children, left child and the right child. And again, this should be a binary search tree in its own. Now this is the left side of the tree, but it should be a binary search tree only. That is, 3 is there on as a root now. So value on the left hand side of the 3 should be less than 3, and value on the right hand side of the 3 should be greater than 3. Okay, like this. Now here if there is no child, you can have any value for the root. If there is a child, then root value is suppose 5, then left child should have value less than 5 strictly. Similarly, here suppose the root value is 5, root node value is 5, then right child value should be greater than 5, like this. Okay, so this is the condition. So this is only told in this. These are the binary search tree properties, that is left subtree of the node should contain value lesser than the root node value, and the right subtree of the node should contain greater than the root node value, and the left and right subtree each must also be a binary search tree on its own, like this. See this part is a left subtree of the original tree, but it is also a binary search tree in its own. The value lesser than 3 is present at the left side and value greater than 3 is present at the right side. So this is also a binary search tree on its own. So now next we'll see why binary search tree is used. It allows fast insertion, removal and lookup of items. Any data is there in the binary search tree. Suppose if I draw binary search tree like this, it may not be balanced or it may be balanced. Now this is a balanced binary search tree. Balance means what? These are called as leaf nodes. So all the leaf nodes should be at the same level. Then we can call it as a balanced binary search. Leaf nodes means those who are not having any children. These are called as internal nodes because it has a children. Internal node always has a children, and on top whatever node is there, it is called as root node. Now this is a balanced binary search tree. It may not be balanced always. So it allows fast insertion. It is always easy to insert the elements in the binary search tree as compared to other data structure. Removal of elements is also very easy. You can easily delete the element from the binary search tree, and lookup of item, that is accessing the element or searching for the element, is also easy in the binary search tree. So that's why this data structure is used. Then efficient way to iterate items in the sorted order. Elements are always in the sorted order. When you try to traverse using in order traversal and all, you will get that elements are stored in the sorted order because left side of the root is always smaller than the root and the right side of the root is always greater than the root. So if you apply in order traversal to this, you will find that elements will be given in the sorted order. So that is the advantage of using binary search tree in data structure. Now we will see one example on binary search tree. We will insert the elements in the binary search tree and we will try to traverse. So we have to create the binary search tree using the following keys. Now these are the keys given, or these are the items, or you can say the data elements given. Using these data elements, I have to construct a binary search tree. So I have to put this data or elements in the binary search tree data structure in the efficient way and in the organized way. So how I am going to put it? Take the first element, that is 5, put it in the node. The circle represents the node. So 5 is the root element now, or you can say the root node because it is there on the top. Now it is a binary, name is only given binary. Binary means two sides. Okay, so bi, from this name only you should know, bi means two, bi-directional, two sides it should have. So left side and the right side. Now 3 is the next element after 5. Is 3 less than 5 or greater than 5? It is less than 5. Okay, all the greater elements will come on the right hand side of 5 and all the lesser elements than 5 will come on the left hand side of 5. So 3 is, we all know, lesser than 5, so it will come on the left hand side of 5. So now 3 is done. Now next is 2. 2 is also less than 5, so it will also come on the left hand side. Now again check whether 2 is less than 3 or greater than 3. It is less than 3, so again it will come on the left hand side of 3. Okay, next is 7. Now 7 is greater than 5, so it will come on right hand side of 5, like this. Next is 4. Now 4 is again less than 5, so it will come on left hand side of 5, but it is greater than 3, so it will come on right hand side of 3. Okay, this is a left subtree and here it will be a right sub. So this is a right subtree and this is a left subtree. So next element is 8. So 8 is greater than 5 and it is greater than 7 also, so it will come on the right hand side only. Elements greater always come on the right hand side. Then last is 6. 6 is greater than 5 but less than 7, so it will come on the left hand side of 7. Of course it will come on the right hand side of 5 but left hand side of 7. Okay, now if you see the left subtree and right subtree also, they are on its own forming a binary search tree because 3 is the root node, value lesser than the 3 is coming on its left and the value greater than 3 is coming on its right. That is 4. Similarly, if you see the right subtree, root node is 7, value lesser than 7, that is 6, is coming on its left, and value greater than 7, that is 8, is coming on its right. Okay, so they are on its own are binary search tree, and overall if you see the root node is 5 and all the values lesser than the 5 are coming on its left and all the values greater than 5 are coming on its right. So overall we have constructed the binary search tree, or we have inserted the elements inside the binary search tree now. These were the elements given and I have inserted all the elements in the binary search tree. Okay, so you can traverse this element by using 3 traversal techniques: in order, pre-order and post order, videos for which I'll be making shortly. So this was all about the example on binary search tree. Thank you.